Welcome, Mrs. DeMink here with the first of a few podcasts dealing with chemical equilibrium in Chapter 15, where we'll be discussing equilibrium calculations, everything down to Le Chatelier's principle. So let's get started with our definition of chemical equilibrium. It is a dynamic state where the rate of the forward reaction equals the rate of the reverse reaction, and this takes place in a closed system. So there is no change. So what that means is there's no change in the macroscopic properties, meaning concentrations. So when we're looking at concentrations of solutions, we'll be talking about molarities. When we're looking at concentrations of gases, we'll be looking usually at pressures. So we'll see both of those two things. When two reactants are mixed, the concentration of the products is 0. And then as the two reactants mix, they react to form products, and the concentration of products increases. As the product increases, the rate of the reverse reaction must also increase. At some point in time, more products are formed from the forward reaction, and they have sufficient concentration to then turn around and cause the reverse rate of the reaction. And equilibrium is reached when those two rates become equal. It doesn't matter from which direction we approach equilibrium, at some point those two rates will be equal. Here's a couple examples of what a reaction at equilibrium looks like. So the first one is called the contact process. It's a huge industrial process involving in manufacturing of sulfuric acid, which is used in fertilizers, paints, detergents, fibers, feedstock for other chemicals. So it's a big industrial process. The Haber process is also used in the manufactures of fertilizer and, importantly, in the production of nitric acid, which can be used to make all kinds of different explosives and so forth. So these are both economically two very important reactions, and are symbols or are reactions that are found at equilibrium. So how do we know that they're at equilibrium? Well, notice this double arrow right there. That indicates that a reaction is going both in the reverse, going sulfur dioxide plus oxygen gas makes sulfur trioxide, and in the reverse, forward and reverse. Don't know what I just said there. So once a concentration of the products is sufficient, it will turn around and start to form the reactants. Now, as chemists, we are interested in the products of our reactions, not so much the reactants. So we want to know how the amount of products compares to the amount of reactants. This is the idea behind the equilibrium constant. So the equilibrium constant gives us that mathematical expression of our position of equilibrium, that ratio of products to reactants. What we have to start with, of course, is our balanced chemical equation. The only time that we really use these equilibrium constants is when we do have this reversible reaction. It is established for a specific reaction and given any specific set of conditions. And the only thing that can really change the equilibrium constant is temperature. So let's see, how do we set up the equilibrium constant? So it kind of looks like this. It's products over reactants. So we're gonna take concentrations of our products and divide it by the concentration of our reactants. So notice what we've got going on here. We have our balanced reaction, and the little j, the little k, n, m, those are referring to, of course, the coefficients. As we take our concentrations, the brackets mean concentrations, and these concentrations are then raised, their exponent is the coefficient from the balanced equation. States of matter. You're going to have to pay attention to states of matter. The equilibrium constant includes gases and aqueous states of matter, but not solids or liquids. And that's very important. Solids and liquids tend to maintain, they call it, it remains at unity. Their concentrations do not really change throughout equilibrium, but gases and aqueous species are affected by a system that is at equilibrium. So what does it mean once we get our value of K? If your K value, your equilibrium constant, ends up being greater than one, it means the position favors the products, that the reaction is going more towards completion, lying towards that side of the reaction. If K is less than 1, then it favors the reactants. So not much is happening. You have small concentrations of the products. If you're pretty close to 1, then you're basically kind of half and half. Equilibrium does not mean equal. It means that the rate has not changed. So unless your K value ends up being 1, you know you're not going to have a 50-50 split between reactants and products. The other thing that I want to show you is that there's lots of little subscripts that you'll see that kind of come along with K. Last year we talked about KEQ. It's sort of a general equilibrium constant. I've already introduced, as you've seen, Kc. That's referring to our concentrations. So when we have molarities of solutions. Kp we use only with gases, and then as we move into acids and bases we'll be using Ka, Kb, Kw, the dissociation of water, and then Ksp for these things that are insoluble but slightly soluble with water. So how do we get back up here? If we're talking about reactions where gases are present, many times Kp is going to be more useful than a Kc expression. So in your notes I give you an example of the Haber process right here and what a Kp expression would look like as opposed to a Kc expression. It's exactly set up the same way, products over reactants. The coefficients then become your exponents, and notice that, but you'll see P instead of just brackets. So that's just a little bit different notation when we're talking about a Kp expression. If you have a Kc expression, you can figure out your Kp value by using our gas loss constant. So here's this little relationship between Kc and Kp. If you have your Kc value and you multiply it by your gas loss constant, R, so you should remember that from previous units, and you multiply that by T in your temperature, and temperature, just like with gas laws, is going to be in Kelvin, and you raise that to the power of delta N. Delta N refers to a change in moles, but just of the gas. Change in moles of gas only. So again, pay attention to those states of matter. Okay, so we've threatened some calculations with KEQ. I give you a few little steps to consider. Of course, we're going to start out with our balanced equation. We're going to use something we call an ICE table, and I'll show you how that works. It's very similar to the BCA table, which is kind of why we did those earlier on. We shift the equilibrium by subtracting and adding x to either side of the equation. You're going to need to do a little bit of algebra, and how you solve for x kind of depends on where your comfort place is. There is a little shortcut that may apply, and I'll show you an example of that. There's a solver function on your calculator if you know how to use that to solve for x. If you don't, be glad to show you that. And just be flexible. Be aware that you might have to do things in reverse of these steps. The final thing to keep in mind is that your answer for x is not likely your final answer. Always make sure that you read the question and the situation and decide what your final answer actually needs to be. X might just be a stepping stone to get to that end point. So here's what an ICE table looks like. If you kind of remember from the BCA tables, we are going to set it up like this, where we have I, which means initial. C stands for change, and E is when your situation is at equilibrium. Now we're going to be comparing concentrations. So we're going to take our concentrations of our reactants on the one side, and in my examples I'll kind of show you how I use the balanced equation to sort of organize my ICE table. But this is just sort of a general format where you have reactants and products. Your reactants, this initial concentration, I'm going to draw some really straight lines here so you can see the table format. Your initial concentration of the reactants is usually going to be given in the problem. Okay, so this is kind of like listing your givens. Your products are usually going to be 0. Your initial concentrations are usually going to be 0. We will run into situations in other chapters where it is not. Change. In other words, how is the concentration changing? This is always going to be some sort of negative value. It's going to go down once the reaction begins. Your product concentrations will always be a positive value. You start with 0, there's only one way to go, and that's positively. At equilibrium, you're subtracting these two values, your initial minus the change for the reactants. For the product side, we're going to do initial plus the change on the product side. And that is what an ICE table kind of looks like. So in the next podcast, we will take a look at several examples, and we'll kind of walk through some math, and this will be a very valuable tool for us as we work our way through equilibrium and then further into acids and bases.